Hello and welcome to Module 3, which is PMED Rehabilitation Design Concept of the Principles and Application of the BcT, or Back Calculation Tool, for Rehabilitation Design using the PMED software course. Let's revisit the course roadmap. In Module 2, we've discussed the fundamentals of deflection testing procedure using FWD, how the back calculation is performed, simulating pavement layers with estimated thicknesses using GPR or coring. In this module, we'll take our discussion one step further by demonstrating how different pieces of information obtained from the back calculation procedure is used during pavement rehabilitation design by PMED. There are 5 learning outcomes from Module 3. These include being able to define the 3 input levels, which is Level 1, 2, and 3 of pavement rehabilitation design included in the MEPDG. Describe the pavement evaluation program to determine the in-place fatigue damage of the existing pavement. List the steps needed for selecting and designing a flexible or asphalt pavement rehabilitation strategy in accordance with the MEPDG. List the steps needed for selecting and designing a rigid or concrete pavement rehabilitation strategy in accordance with the MEPDG. Finally, discuss the use of FWD deflection basins and back-calculated elastic layer moduli for flexible and rigid pavement design. The topics that will be covered in this session are overview of different rehabilitation design input levels used in the PMED and identify the differences between the rehabilitation input levels 1, 2, and 3. Discuss the FWD testing and back calculation of elastic layer moduli for flexible and semi-rigid pavements. Also discuss how FWD testing and back calculation of elastic layer moduli is performed for rigid pavements, JPCP and CRCP. Information included in this module applies to all pavement types for rehabilitation design. This includes flexible pavements, rigid pavements such as JPCP and CRCP, and semi-rigid pavements. Let's start with an overview of pavement rehabilitation design in accordance with the MEPDG or PMED software. For any rehabilitation project, completing an assessment of the pavement and adjacent features is important to select a proper design strategy and determining the layer thickness. The adjacent features to be used in rehabilitation are covered in the MEPDG Manual of Practice, but the 2 more important ones are drainage and shoulders. Module 3 focuses on the structural condition of the pavement itself and not the adjacent features, but the condition of the adjacent features should be used in selecting an adequate rehabilitation strategy. For the structural assessment using FWD testing, the types and causes of the distresses should be defined. Now let's review the MEPDG rehabilitation input levels for different types of pavement. For asphalt and semi-rigid pavements, Level 1 requires the back-calculated elastic layer moduli for the asphalt and other layers from deflection testing. Level 2 needs the amount of fatigue cracking, transverse cracking, and rutting from the visual distress survey, and Level 3 only requires a subjective condition rating, such as structural and environmental. We will not go into detail on these input levels, as this topic is covered in an MEPDG training course, Module 9, Flexible Pavement Rehabilitation. For rigid pavements, there is no separate input levels for rehabilitation design. The MEPDG only needs the slab condition and transverse joint load transfer efficiency, which is LTE. However, results from the deflection testing program can be used to supplement the input values to the PMED software for rehabilitation design. Again, this topic is also covered in MEPDG Training Course Module 8, which is Pavement Rehabilitation. There are different input levels for flexible and semi-rigid pavement rehabilitation design. Level 1 needs non-destructive deflection testing and back calculation of elastic layer moduli. Back-calculated elastic layer moduli defines the in-place fatigue damage of the asphalt layer for rehabilitation input Level 1. The concept for use in rehabilitation design is to associate the back-calculated elastic layer modulus of the asphalt layer to the amount of bottom-up fatigue cracking you can see at the surface. The photo on the left shows no bottom-up fatigue cracking, so the back-calculated elastic layer modulus should be higher than for the 2 conditions or amount of bottom-up fatigue cracking that's shown on the 2 photos on the right. The third, the photo on the right, displays a lot of bottom-up fatigue cracking. So the back-calculated elastic layer modulus should be low and representative of a lot of fatigue damage to the asphalt layer. The correspondence of the back-calculated elastic modulus and amount of damage of the asphalt layer will be explained and defined shortly within this session. Level 2 requires data from surface condition or distress survey and assessment. Level 3 needs subjective rating of surface conditions. As a note, the MEPDG Manual of Practice suggests or recommends that Rehabilitation Input Level 3 should not be used unless no deflection data and no distress surveys have been completed, like what might be done for a preliminary rehabilitation design. This is the process of getting Rehabilitation Design Input Table 1 data for flexible and semi-rigid pavements using FWD testing and back calculation to derive fatigue damage in the existing pavement. FWD testing is performed along the outside wheel path of the project, including cracked areas to determine the damage moduli. However, the longitudinal path of deflection testing is normally defined for safety purposes to keep the FWD device and operator as far from oncoming traffic as possible. The air, pavement surface, and/or asphalt temperature is measured during deflection testing. Remember, as previously discussed in the training course, the asphalt layer temperature is rarely measured during routine deflection testing for rehabilitation design, so it can be calculated using the air and/or pavement surface temperature recorded during deflection testing. Back calculation is performed to determine mean layer elastic modulus along the project. Elastic asphalt modulus determines in-place bottom-up fatigue damage of the asphalt layer. For rehabilitation design input levels 1 and 2 for flexible and semi-rigid pavements, visual distress survey data is needed and required. Types of distress data required are length of transverse cracks for reflection cracked prediction. Remember, the deflection test should be away from the transverse cracks if possible, because the transverse cracks will have an impact on the deflection basin measurements. Any deflection measurements to estimate the load transfer efficiency, which is LTE of the transverse cracks, should be separated from the measurements of areas without fatigue cracks and in areas with fatigue cracks. Deflection tests to estimate the load transfer efficiency will be discussed later in this session. Total rut depth measured at surface for predicting rut depth using strain hardening concept. The total rut depth in the PMED software is assigned a certain percentage to the pavement layers, and the PMED software will continue to predict the amount of rutting in all layers throughout the rehabilitation design period. Other design features and material-related distresses such as debonding between layers, stripping, raveling, potholes, etc. These distresses are used indirectly in the PMED software. This slide and the next 3 slides are included here in Module 3 because it is important to understand the differences between the laboratory measured values and those back calculated with the BcT tool. This slide shows the 2 master curves for the asphalt layers considered in the PMED software for rehabilitation design. Number 1, the modulus for the asphalt layers, and number 2, the back calculated elastic layer modulus for the damaged or deteriorated asphalt exhibiting cracking and other forms of distress. The undamaged modulus is shown by the solid blue curve. The solid blue curve is defined by the laboratory measurements or the default calculated dynamic modulus using the regression equation in the software. So, it is a laboratory-derived master curve without any damage. And the damage modulus, which is shown by the dashed red curve. The dashed red curve is defined by the back-calculated elastic modulus and the reduced time for a frequency of 10 Hz, and the average mid-depth temperature of the asphalt layer. The intersection of the green and purple line in this slide displays one temperature or reduced time and back-calculated elastic modulus value. However, the user or designer can measure the deflections and back-calculate the elastic layer moduli at multiple temperatures during the same day or on different days to estimate the impact of temperature on the damaged master curve. The PMED software uses all temperature-dependent asphalt layer moduli to estimate the damaged master curve. Bottom-up fatigue damage is related to the difference between the modulus for the undamaged and damaged curves, displayed by the solid black arrow between the 2 curves. The equations included in the PMED software for calculating the dynamic modulus undamaged and damaged master curves are not included in this module. The equations are included and explained in the MEPDG training course within the asphalt module. As a note, it is possible that the FWD back-calculated elastic modulus will be greater than the undamaged generic modulus. If and when this occurs, the PMED software simply assumes the asphalt layer exhibits no damage and uses the undamaged curve, the solid blue line. The previous slide focused on the asphalt layer. Now let's focus on the unbound layers. Specifically, to answer the question, is the in-place back-calculated elastic layer modulus of an unbound layer equal to the laboratory measured resilient modulus of that unbound layer? Back calculation of unbound elastic layer moduli are estimated at the in-place volumetric and physical condition of the unbound layer. However, laboratory resilient modulus testing is normally performed at the optimum volumetric properties of the material. So, there is a potential difference between the default resilient modulus values measured at optimum conditions and the back-calculated elastic modulus values determined at the in-place condition, because the physical condition of the unbound layer or material is different. If there's a difference, which there is, how does the PMED software take the difference into account? The next couple of slides illustrate that difference and provide some of the options to be considered in the PMED software. So, what can be done to reduce the variability between back-calculated and laboratory-derived resilient modulus? The relationship between the back-calculated and laboratory-derived resilient modulus from the 1993 AASHTO Pavement Design Guide, which is designated as the C value, is used to relate field-derived moduli to those derived from laboratory tests. This correction factor C in the equation generally ranges from 0.35 to 1.25 for subgrade soils, depending upon the pavement structure. Again, by controlling the factors discussed in the last slide, laboratory and field-derived moduli should be nearly equivalent. To summarize from the previous slide, the elastic modulus back-calculated from the deflection basins represents the load response from the in-place unbound layers, a specific water content, and dry density. The laboratory-measured resilient modulus, at least the default values, represents the resilient modulus of the material at the optimum water content and maximum dry density. The AASHTO C factor, which has been used or has been in place since the 1993 and earlier AASHTO Design Guide versions, is used to adjust the back-calculated values to the laboratory-derived values for the same in-place volumetric condition, water content, and density of the unbound layers. Applying the C factor to the back-calculated elastic modulus values is a conversion to a laboratory equivalent value, but at the in-place volumetric condition, the MEPDG Manual of Practice and Training course provides additional information and references for the C values to convert or translate the back-calculated elastic modulus to an equivalent laboratory-measured resilient modulus at the same volumetric condition. But the in-place physical or volumetric condition is probably different than the optimum physical condition used in the laboratory resilient modulus testing to determine the default design resilient modulus values for different unbound materials and soils. If the user or designer is using the default laboratory-derived resilient modulus values in rehabilitation design, an additional adjustment is needed to convert or translate the in-place physical volumetric condition to a resilient modulus at optimum physical or volumetric condition. The next slide provides discussion to the user so it is understood that what water content and dry density of the material or soil that are entered to be compatible with the back-calculated elastic layer moduli are adjusted to the laboratory conditions. So as not to confuse anyone from the previous slide, the PMED software for Rehabilitation Input Level 1 requires a C factor to be entered by the user. From the previous slide, the C factor converts or translates the back-calculated elastic layer modulus of unbound layers to a laboratory equivalent resilient modulus at the same volumetric conditions during deflection testing. The C factor ranges from 0.35 to 1.25 for subgrade soils and aggregate base layers depending upon the pavement structure, but is not material or soil type dependent. Understand the C factor does not convert the back-calculated elastic modulus values at the in-place volumetric condition to optimum conditions. If an agency used laboratory modulus values for calibration, which were at optimum conditions, and does not routinely measure the in-place water content and dry density, an additional conversion factor needs to be used to convert the back-calculated elastic layer modulus values at in-place conditions to a laboratory-derived resilient modulus at optimum conditions. This value in the slide is defined as C suboptimum. In summary, and very briefly, how does this relate compatibility of the inputs to the PMED software for rehabilitation design input level 1 designs? Many agencies measure and use the in-place water content and dry density of the material or soil, so the only conversion that is needed is the C factor. In other words, the water content and dry density properties of the layer material or soil entered in the PMED software are the in-place physical conditions. The software starts at the in-place conditions and then adjusts the resilient modulus as the volumetric conditions change over time from the values defined at the time of deflection testing. A few agencies use default optimum conditions during calibration and forward design, and do not routinely measure the in-place water content and dry density at the time of FWD testing. For this use, the default volumetric properties are needed, so an additional conversion factor, which is illustrated as C suboptimum factor in the slide, is required. In other words, the water content and dry density properties of the layer material or soils entered in the PMED software are the optimum water content and maximum dry density defined by the agency. The total adjustment value derived by a few agencies are 0.55 for fine-grained soil and 0.63 for coarse-grained soil. The important point here is to make sure that you are using inputs that are compatible. Agencies that routinely measure or estimate and enter the in-place water content and dry density at the time of FWD testing only use the C factor and enter the back-calculated elastic layer modulus and in-place water content and dry density. Those agencies that do not routinely measure the water content and dry density of the unbound layers at the time of FWD testing and use or enter the default optimum water content and maximum dry density use the combined factor or C multiply C suboptimum. The previous slides focused on flexible and semi-rigid pavements for rehabilitation design. Now let's move our attention to rigid pavement rehabilitation design. As stated earlier, for rigid pavements, there are no separate input levels for rehabilitation design. The user or designer only needs slab condition and transverse joint load transfer efficiency, or LTE, from visual distress survey, FWD deflection basins, and back-calculated elastic layer moduli provide supplemental information for strategy selection and any pre-overlay repairs as part of the rehabilitation strategy. Just like for flexible and semi-rigid pavements, the in-place damage of the existing PCC layer is determined by the software from distress survey. The PMED software determines damage of existing PCC from distress values entered and then accumulates additional damage of PCC layer from the starting point. For JPCP, it is performed through percent cracked slabs, see the figure at the left. The percent cracked slab and/or repaired slabs are entered and the PMED software determines the in-place structural damage using the calibration curve between cracked slab and fatigue damage index. For CRCP, it is done by number of punch-outs per mile. See the figure at the right. The number of the punch-outs per mile are entered and the PMED software determines the in-place structural damage using the calibration curve between the number of punch-outs and fatigue damage index. The PCC back-calculated elastic layer moduli are not used in the determination of the in-place fatigue damage index. The next few slides provide the reason why the back-calculated elastic layer modulus are not used directly by the PMED software. As illustrated from the previous slide, the fatigue damage of the PCC slab is defined from percent cracked slabs from the distress survey for JPCP. However, back calculation of the elastic modulus of the existing layer is and can be routinely performed. So how are the results from the FWD deflection used in rehabilitation design for rigid pavements? For the different layers of a rigid pavement, back-calculated PCC slab elastic modulus are used for information purposes and rehabilitation strategy selection. For unbound layers, the back-calculated elastic modulus are treated and used as the same as for flexible pavements. For asphalt base and overlays, the back-calculated elastic modulus are treated and used the same as for flexible pavements. The graph displayed on this slide includes the relationship between the average 28-day modulus of rupture and average 28-day elastic modulus of PCC mixture that is included in the PMED software as displayed by the solid black line. The data points displayed in the graph are actual values measured in the laboratory for a range of PCC mixture for an agency. As displayed, there is a consistent difference between the two. So, there can be a bias or a consistent difference between using the regression equation in the PMED software and laboratory measured values. Elastic modulus and the modulus of rupture have a significant impact on the fatigue cracks predicted by the PMED software for PCC pavements, so there will be a difference between the two input levels displayed on this graph. Just like for flexible pavements, there must be data input compatibility for rigid pavements. So, the flexural strength of the PCC layer must be compatible with elastic modulus of the PCC layer entered in the PMED software. The MEPDG recommends that the 28-day modulus of rupture and the 28-day modulus of elasticity be used for the PCC as a starting point. The time-dependent modulus of rupture and elastic modulus can also be used as input level 1, but the times need to be the same between strength and modulus of elasticity. These are for an undamaged PCC layer. This slide is basically a review of some of the information presented in the PCC Inputs module of the MEPDG training course because of the interrelationship between strength and modulus of concrete and its importance in predicting different distresses of rigid pavements. So before continuing, some questions are: what is the impact on cracking if PCC strength increases and the elastic modulus does not change? As strength increases with no change in elastic modulus, there is an increase in performance or a reduction in mid-slab cracks for JPCP and a reduction of punch-outs for CRCP. Next, what is the impact on cracking if the PCC elastic modulus increases and the strength does not change? As the elastic modulus increases with no change in strength, the stress in the slab increases. Without an increase in PCC strength, the performance will decrease or the amount of cracking and punch-outs will increase. What is the impact on cracking if the elastic modulus and strength of the PCC mixture increase? As the elastic modulus and strength increase, the impact of cracking may increase or decrease. It really depends on how the strength increases relative to the elastic modulus as displayed in the figure. Another variable is the CTE, coefficient of thermal expansion. What is the impact on cracking if the CTE increases? As the CTE increases, the amount of cracking and faulting will increase because the slab will exhibit a greater change in length with temperature changes throughout the slab. The following slide includes some examples of the back-calculate elastic modulus for different PCC layers and their condition. The first example is an asphalt overlay on fractured PCC slabs, which comes from the long-term pavement performance experiment. Fracture, as defined by the MEPDG, is divided into two categories. First, crack and seat JPCP slabs. Second, rubbleized JPCP and CRCP. The figure in the slide graphically displays the back-calculated elastic layer modulus over time for three conditions: an intact PCC slab, a crack and seat section, which is represented by the green triangles, and the rubbleized PCC section, which is represented in the graph by yellow circles. The back-calculated elastic layer modulus of the PCC layer represents the mid-slab condition, no deflections across joint or cracks at the time of FWD testing as displayed on this slide. The back-calculated elastic layer modulus is between 6 to 6.4 million psi many years after original construction of the JPCP prior to overlay. Use of the 28-day modulus of rupture and 28-day modulus of elasticity would result in incompatible inputs for the PCC slab. Thus, the strength or modulus of rupture and modulus of elasticity must both represent the same time of testing for intact conditions. The PMED software cures the PCC layer after construction. So, the MEPDG suggests that 28 days strength and modulus values be used or in accordance with how the PCC fatigue cracking relationship was calibrated. The modulus of elasticity for this crack and seat section varies from 600,000 to over 3 million psi. For the crack and seat strategy, only the modulus of elasticity of the fractured layer is needed. Strength is not needed because the PCC slab is assumed to be fully damaged. No additional fatigue cracking is predicted. The modulus of elasticity for the rubblized section varies from over 100,000 to over 200,000 psi. For rubbleization strategy, the rubblized PCC layer is assumed to a high modulus aggregate base in a new flexible pavement design. We'll not go into details, but the reason behind the high elastic modulus of crack and seat is the largely spaced controlled cracks which have more solid concrete surfaces compared to the rubblized one, which is completely shattered to small pieces of concrete. The MEPDG training course goes into more details about the PCC rubblization design and how they are simulated in the PMED software. This is another example from the long-term pavement performance experiment, and the slide displays the back-calculated elastic layer modulus of the PCC layer for rehabilitation design for rigid pavements of different conditions. This figure indicates that AC overlay or intact or solid concrete pavement has a higher elastic modulus than a crack and seat rehabilitation. As we discussed in the last slide, crack and seat has largely space-controlled cracks, so asphalt overlay is designed using a reduced elastic modulus for the cracked PCC slab. Typical elastic modulus for cracked slab is around 1.5 million psi. For design input compatibility, the asphalt overlay of an intact PCC slab is the focus. The modulus of elasticity back-calculated from the FWD deflections measured on the slab interior represent the elastic modulus many years after original construction, while the PCC modulus of rupture is usually unavailable. So, the inputs to be used in the PMED software are the 28 days strength and modulus values. They must be compatible to get an adequate estimate of the fatigue damage. In summary, the modulus of rupture and modulus of elasticity for any PCC slab must represent the same time which was used for calibration. The back-calculated PCC elastic modulus values are only used indirectly to select a proper rehabilitation design strategy. Some supplementary information can also be obtained from FWD testing for rehabilitation strategy selection and design for all pavements. The first is for voids detection or layer disintegration. The standard procedure for this purpose is outlined in the AASHTO 1993 Pavement Design Guide. It was developed and used for rigid pavements to select a proper rehabilitation design strategy. However, the void or layer disintegration has been recently applied to flexible pavements to identify potential areas with severe stripping and other layer defects. The second is for estimating load transfer efficiency of transverse cracks and joints. The LTE, as defined by LTPP for rigid pavement, the equation shown on this slide is how the LTPP program applied it to measure the load transfer efficiency of PCC joints. However, a second equation has been applied to flexible pavement for estimating the load transfer efficiency of transverse cracks. Just to recap the topics we discussed about rehabilitation design input level 1. For asphalt and semi-rigid pavements, FWD deflection data from non-destructive deflection testing and associated back-calculated elastic layer modulus provides primary data, while distress survey data provides supplementary data. Whereas for rigid pavements, such as JPCP and CRCP, distress data provides primary data. FWD deflection data and back-calculated elastic layer modulus provides supplementary data. And for your reference, the topic is covered in MEPDG Training Course Modules 8 and 9, Rigid Pavement Rehabilitation and Flexible Pavement Rehabilitation. This ends Module 3. The next module of the training course is Module 4, Session 1, which is on accessing the BcT software. Thank you.